Okay, so here's a little overview of all the details of the LC3 simulator. You can see if you just go to LC3 simulator online, it will come up at the top one, and you look for this charge in or whatever the name is that has this simulator. And so you see on the right here, there's a panel here or a pane here with registers, and you can, if you hover your mouse over each one, you'll see that it tells you what the decimal is, although the hex. So if we put in here the hex value of, say, 14, which is the decimal number 20, right? Because it's 16, you'll see the 20. So it automatically does the conversion for you. But that's not really, that's helpful. And the fact that you can modify the registers is useful. And is at some point, if you might want to reset the registers. Now, if you have a program, resetting the registers sets it back to where it doesn't erase your program. For example, the original PC counter is going to be wherever you started it. And this blue thing over here, so you can move the PC count. Some of this stuff, like setting breakpoints, we'll only use when we get to assembly language, right? Because we're not really doing programming as such, so we don't really need to debug the programs because I've already written them for you. So you move the PC counter here. You can do that, or you can reset all the registers. Resetting the registers isn't the same as clearing. This one doesn't clear this, but it does clear the 8 registers up here. There's a console here, right? And down here's where you click raw to put your program in. This is the memory. So you have basically you have an array over here, an array over here, and this is the address, and this is the content. Okay, so I can edit this and just put numbers in here. This NOP, it tries to interpret what the instruction is. NOP is no operation. Sometimes, though, you put in data, right? And the program will try to interpret your data as an operation. So if you, I'm not sure if I can reproduce this, but it may be that if you put in 1, 2, 3, 4, see it, well, it happened to be an instruction. But this had nothing to do with this instruction. So the fact that it's doing this instruction is misleading, right? It gives you sort of the format, add R1 to R0 with -12. And who knows how that came about, right? But anyway, so so this can be misleading. Further, one of the, let me see, let's say that sometimes you have like data. Let's say you had data at 4000 C and you wanted to see what it was after your program ran. You can put in here X400, see, and it 0, and it takes you to that address, right? Now, if you then put another number in 3000, it takes you back. So you can sort of move around in the memory to look and see. And sometimes you want to put data to test your program at certain locations. So you can move around there. This CC again is the capital NZP. It shows you which one is 1, right? Because of all the capital N, capital Z, capital P, only one can be 1, the rest are 0. So it tells you which one is 1. You've got the registers, but the PC counter, but the instruction register. This is the number we're never going to deal with, PSR. It's actually, there's built-in support for an operating system in which there's 2 modes. There's sort of like user mode and protected system mode. And the protected system mode is the one where you would have a certain region of memory protected from user access, and that you'd put your operating system there. The operating system, you can see, is basically a set of calls that deal with peripherals. Okay, and they're at the machine language or assembly language, they're called trap calls, because what they do is they trap certain memory cells and they connect to other things, okay? And they're called system calls when you get to an operating system level. You can see what system calls are available by clicking on manage labels. These addresses are where the code is, but we don't access it with that address. We access it with a trap vector. So, for example, you know the trap vector is x25. Well, we'll go and do that in a second. So the trap vector, we know about halt, right? Well, it's up here, this weird place, FD70. We know the trap vector was trap x25, right? Well, let's put in x25, and you can see that there's an address here, FD70, right? Well, FD70. So when you put in the trap, so the trap vector takes you to an early table here where you have like 25 takes you to this address, and at this address there's some code. That's the halt. Now the reason halt's up here is because what halt connects you to is the clock. Halt turns the clock off. There's a finite state machine that's running, so it just stops the machine. The other problem is that halt's a subroutine and it uses registers. So when you call halt, it messes with these registers. Okay, so in our early programs, if you want to see what the registers are, you can step through the program. Now, if we go back to, let's see if we go up here, you can see there's some other numbers in here, right? Let's see if we go a little bit higher. X20, so the X20 is no op, but then here you can see that now it's not really a branch here. These are addresses. So look at 430 is X21. If I come over here, I have 430 is trap out. Well, trap X21 is the trap vector for out, for sending a character to the console. And the way that you communicate with the keyboard and the console is always through register 0. So if you put an ASCII code in register 0 and then call out, what it does is it reads the character that's in R0 and sends it to the console here, right? So, and then you see it. And this is how you get, and the same thing, when we, at some point there'll be, there's trap in, which gets a character from the keyboard and puts it in R0, so your program can read input from the program. So well, it's going to be easier to do input-output when we get to assembly language, when we don't have to, so there's certain things, resources that right now in your program, you'll see, I think, and there was a puzzle with a trap in and trap halt. And there's also one that puts a string, right? This gets a character and prints a message, trap out, put S in. I'm not sure what the point of this one is. But this one deals with the clock. The rest of them just deal with the console. So that's our only peripheral is the console here. So the only system calls mess with this. This is sort of like a baby version of a terminal on Vera Virtual, right? If you were writing an operating system, the first thing you do would be write a terminal program so that you could send commands back and forth and write a text editor so you could edit things. And once you do that, then you could use the LC3 to write, basic stuff. Okay. So that's how you, the one other thing about the LC3 is these buttons here, right? Well, if you look at step, it says execute the next instruction, entering a subroutine if necessary. So let's say you had your program had trap in and you wanted to step through it. Well, trap in is a little subroutine that's a separate piece of code that your program goes, executes that code and comes back. Now, you're not really interested in looking at the code of trap in. You'd like to just jump over it and come back to your program. Well, steps into the program. So, but then next says fully execute the next instruction or subroutine. So if you wanted to jump over, if you were at trap in, you could just call next and it would execute the whole trap in and go to the next line of your program, rather than you having to walk through all the code that's in the subroutine. Now, let's say you click step when you meant to click next so that you started the subroutine. Well, then you can continue, and what it does is continue, no, not continue, finish. Finish execution of the current subroutine. So if you step when you wanted to go skip over the subroutine and you're in the subroutine, you can click finish and it will do the same thing as you've gotten back to next. So you can use these things to step through your program, even if you have a trap call that you don't want to look at. Then continue has to do with pausing, and then once you halt, you have to unhalt. And then if you just want to run everything until you come to a halt, you click on run. It just runs indefinitely until halt comes. If I run here right now, what it did was it ran all the way through the memory up, like the final memory is FFFFF. Well, look what here. So I just ran, it just tried to execute every single and the first execute was 0. See, if you didn't put an instruction, if there was 0, it didn't do anything, right? But the clock ran, it loaded the 0, incremented the PC counter to 3001. So in that little time, it went through and executed 0 65,000 times or so, and came to trap halt at the end. And then down at the end here, there's some special registers for input and output that we'll come to when we do with assembly language. And you can see here, this is the code for trap halt in here. It's a little subroutine. Okay, so then if you want to come back here, then you come back to 3000. And then since you've halted, if you want to reset the machine, you can halt. Then you could, let's say you want to just bring it back to here, move PC counter here. You could also move the PC counter into the middle of your program and run a particular instruction to see what it was doing. So you can use this, you can see here, you can use this to just setting the breakpoint, just puts a point in your program where the code runs up to that point and stops. It can be used to debug things, but we don't have to worry about that until we come to assembly language. Well, that's next week, so it's not too far away. Okay. So that's all I really wanted to say. So I think, let's see. I think I can